Okay. Now, for this lecture, we're going to introduce the interaction of electromagnetic waves with the atmospheric constituents. So, before that, we're going to take a brief introduction about the atmospheric layers around about the Earth. So from the sea level, actually, and so for the detection by the radiometer, we usually use two kinds of mechanisms. The first one, it is based on the atmospheric transparency. And another mechanism is the atmospheric opacity. So the first one is when the radiometer wanted to observe the properties of the land, ocean, or space, or air. So it needs to propagate the road atmosphere. So it needs the transmitter, all right, of the transmission. Another one is the opacity. Is because when we wanted to observe the atmospheric constituents. So we hope it's gonna give us the backscattering components. And we need know as opacity instead of the transmitter, right? So for the transmittivity, there are for the atmosphere, they are almost transparent for the microwave ranges around 1 to 15 gigahertz. Mostly in this frequency range. And besides this frequency range, there are some sharp absorption lines. This can block the propagation of the electromagnetic waves. So for an example, in the for the constituents in the atmosphere, they are water vapor, and also oxygen, so for the water vapor, it has several absorption lines, all right? And mostly for the electronic absorption, it has, the first one is at around 22 gigahertz, and another one is at 183 gigahertz, the absorption lines. Absorption peaks. And for the oxygen, it has several absorption lines. The first one is in the range of 50 to 70 gigahertz. Another one is 118 gigahertz for the absorption peaks. So when we wanted to, for example, monitor the water vapor density or the relative humidity of air, we would usually, the best thing is we employ the electromagnetic waves operating in this, at these two frequencies. And for if we wanted to monitor the oxygen components, we can employ the frequency range at these frequency points, or the frequency range here, and used for that one. So for example, there are many experiments in the pool, right? The North Pole, the South Pole, want to monitor the oxygen in our atmosphere. So we can put the frequency range, the radiometer operating at 118 gigahertz for monitoring and detect the content or the concentration of oxygen, and by measuring the absorption lines or the line strength. So, because the line strength is usually emerged in the absorption peaks by other atmospheric components, so the best thing is figure out all the pollutions. So the best thing is to figure out a position that the air is relatively clean and not, and with the altitude, with a high altitude, and so you can get a better observation of that by this system here. So for the when we look at these points, we can see it is from 1 to 90 gigahertz, and there are several absorption lines by the oxygen. For example, the black line, and here, this is the 50 to 70 gigahertz, and another one here. So, and for the water absorption lines, there is one at 22 gigahertz, and here, this one is 183 gigahertz. Yeah. So for the observation of the atmospheric constituents, we already employ these frequency ranges for the detection or observation. And if we want to observe the land, the ocean, or the space, where the electromagnetic waves need to propagate throughout the atmosphere. So we chose these windows. This is going to exert the minimum power attenuation or the signal attenuation. So as we chose this windows, and also maybe this windows, even though it is very hot. All right. So the here we shows it as the downward brightness temperature. So what is brightness temperature? This is because it's related to the black body radiation. All right. So it is related to the passive radiation by the objects, right? So we already used the radiometer for the passive detection, and it has two kinds of there are two kinds of the detection process or the observation process. The first one is what we really the radiometer works. All right. So if we wanted to detect the atmospheric components, constituents, or so we needed to know. It is based on the input, all right? So the first input is the atmospheric variables, such as the temperature profile, the pressure profile, the density profile, and also if there are the weather effects, the rain or snow rate, and the cloud water content and other components together, and the inputs detected by the radiative transformer, the transfer model, all right? So another thing that we need to input is for the radiometer as its own variable, such as the operating frequency and the observation angle, or the elevation angle, or the zenith angle, all right? So the third thing is the boundary conditions here. So for the boundary conditions, for example, we have radiometer, for example, right? So we keep it. Looks like this one, okay? And it is for a downward looking device, all right? So for the downward looking device, if it wanted to observe it is in space, for example, and it is in space carried by a satellite, for example, and it's gonna propagate through the atmosphere, all right? And then onto the ground, or onto the land or ocean, and it gets the feedback, all right? So here is boundary condition. It's based on the what? Because its aperture is downward, so it's gonna collect upward emission from the atmospheric constituents, all right? Upward emission from the atmospheric constituents. So this is its boundary condition, the upward emission. Okay, and for the oppositely, or inversely, for the upward looking device, its boundary condition is for the downward emission, all right? Because the aperture is faced upward here, so it only collects the downward emissions from the atmospheres. Then finally, we get the brightness temperature here. So it is a function of the frequency and the elevation angle. And so this is the detection process by the radiometer. And for us, what we want to do is we usually use the radiometer to obtain the atmospheric variables, all right, to get to observe the performance of the atmospheric constituents. So what we need to do is we get the radiometric observations from the radiometer here. Is evolves with respect to frequency and with respect to the elevation angle, as shown here. And also they need a prior information, for example, about the boundary conditions and some other measurements based on other performance devices, and we're gonna get or obtain the temperature profile and the density profile, pressure profile also, and other performances, the performance of other variables here. So what we want to do is get that one. So here we need a inversion algorithm, all right? So this is how to obtain the estimated variables here. Here is the radiative transfer model inside the device. Or sometimes after our detection, we use some signal processes or algorithms for this part. And when we get that one, we put it as the input of the inversion algorithm, and then we can get the estimated variables here. So this is, and the best thing is the estimated variables agrees very well with the actual atmospheric variables. This is the best thing, all right? And this depends on how the inversion algorithm works. And actually, this is the most difficult thing for us. So this is the detection and the inversion process by using a radiometer for the atmospheric variables here. And so our aim, for example, is to obtain the profiles of the atmospheric parameters. So now, how they perform actually. So for the first thing we wanted to introduce is the atmospheric pressure. So just for under the condition of a standard atmosphere. So this is for a standard atmosphere. As temperature and as pressure, first thing is the pressure. So we use the captain P beta to represent the atmospheric pressure. So the atmospheric pressure, it evolves exponentially, and so when we plot it, and let it evolve with respect to the altitude or the height from the Earth. So, so here is the pressure. In the unit of millibar. And here is the height or altitude. Okay, as in kilometer. So the pressure decreases exponentially with respect to the altitude, like this one. This is what the temperature evolves. And there is a formula to express the relationship between the H, and it can be expressed as the it evolves, decreases exponentially. So it can be expressed as like this one. Evolves exponentially, and it has initial pressure when the height equals 0. So this is this one at sea level, the pressure at the sea level So for the pressure at sea level, we have for a standard atmosphere, its values is around 1013, all right, 1013.25 millibar, all right, 1 atmosphere. So this is the values for it. Equals this one. So this is for the standard atmosphere, and this is just for the pressure. So the pressure it evolves along one simple formula, but the temperature does not follow such a condition or such a trend because it follows a cyclic pattern. And before that, we want to introduce. So when we wanted to before we wanted to analyze the temperature evolution through the atmosphere, we first needed to do is define what is the standard atmosphere. So the standard atmosphere, it is standard. The first thing is it was defined by an international constitute. It is called ITU. So International Standard Atmosphere. Another one is defined or proposed by United States. So it is called US Standard Atmosphere. So there are two kinds of standards. Both have the same definitions for the altitude below 32 kilometers. So they have the same standards here, and above that altitude, they have some differences. Even though it's not very large, because they have their own definitions for each of them. So for the atmosphere, so let's define it again. Here is the altitude, and here is the temperature. So this is temperature T with the unit Kelvin, actually we are used, and this is the altitude. Unit kilometers. Okay. So now we separate it into, it has the length, okay, yes. 0, 10, 20, 30, 40, 50, 60, 70, 80, and above 80, there is a very thick layer, 100, 110, okay, and so the first for the evolution of the temperature near the ground, we really express it as 300 Kelvin, right? 300 Kelvin. That means the temperature in degrees centigrade is around 27, all right? 27, near the ground. And after that, with the altitude increases, it decreases. linear scale. It decreases linearly, and then it keeps a constant with the increasing of the altitude, and then it decreases. It increases with the increasing of the altitude, and then it keeps to be a constant for a while. After that, with the increasing of altitude, it decreases again. And after that, it keeps to be a little bit constant with the increasing of the height, and then decreasing, and decreasing to here. After that, it increases again. This one, very high. So this is the temperature evolution with respect to the altitude. And why it follows such a condition? That's because the atmosphere can be separated to be several different layers, all right? So the first layer here, we call it troposphere. So this layer is called troposphere layer, right? And the bottom of this layer is called tropopause. And so now we can define this layer. There's another layer. This layer is called stratosphere. And it's the bottom of this layer is called stratopause. And this layer, third layer, right, at each turn point, all right, is the separation of the atmosphere. The third layer is called the mesosphere. And the bottom of it is the mesopause. And the last layer is the thermosphere. And it extends to the deep space, okay, until there is no air. So, but we can say its temperature is very high, all right? So, this is the temperature evolution inside of atmosphere, and it depends on which layer it is, all right? And for us, what we usually mostly concentrated is the troposphere, and length is around 11 kilometers here. So, all right, below 11 kilometers, that's what we want to concentrate on. And for the stratosphere, because the air is very small, it flows, right? So that's why the plane, all right, it usually flows in this layer. So it is much more easier to characterize. The most difficult things is here, right? So in this layer, from the ground to the 11 kilometers. We usually can use a parameter to represent the evolution of the temperature, because as we can see that besides the turn points, it evolves linearly, all right? Follows a straight line here, follows a straight line, a straight line, and a straight line. So we're gonna have a parameter to characterize that. It is the rate, right? D theta. the temperature, dt or d theta. All right, and it has its own name. It's called temperature lapse rate. Temperature lapse rate. So for the troposphere, the temperature lapse rate is around 6.5 Kelvin per kilometers for the this one. It should be negative, right? So because it decreases with the increasing of the altitude. Okay, now this is the here the evolution of the temperature, and this evolution is just for the standard atmosphere. Just take remember, because atmosphere is different, the characteristics of the atmosphere at different geometrical locations, right? For example, if it is close to the pool, then it can be a different performance. And if it is close to the tropics, it also gonna be a very different. For example, in the winter, and also varies with the seasons. In winter, the length of the height of the troposphere is around 8 to 10 kilometers. Right? Okay, and if it is in the this is in winter and in Arctic regions. Okay, if it is close to the tropics, so it's gonna be 16 to 18 kilometers for the triple poles. Okay, its length. So the 11 kilometers is just for standard atmosphere. For the middle altitude, the altitude. Okay. The third thing that I want to introduce is the atmospheric components, the compositions. So I think from our middle school, we are familiar with that, right? So the atmosphere is mostly composed by the nitrogen and oxygen, all right? And they are almost 99 around percent to the atmosphere. And so the most important thing is the nitrogen here is around 78%. Another one is 21, or almost or approximately. So this condition is just under the condition that we do not consider water vapor, right? Because the water vapor, it varies almost at different times of the day, at different reasons, and also corresponds to different locations. It's going to be different, and it's complicated, and it depends on our estimate and the local measurement. So this composition is under the condition that we do not consider the water vapor, and also it keeps constant over the altitude or over the height below 90 kilometers. Okay, and they are contained by volume, and almost keeps the constant over from 0 to 90 kilometers. even though with the increasing of the height, their density decreases. And all of them decreases, not just one. So they keeps the ratio almost or always. So for the at sea level, the air density is around, so it is from at sea levels, the height equals 0. It is around 1.225 kilogram per cubic meter. This is just for the because we do not consider the water vapor, so this is for dry air. Okay, this is for dry air. If there are water vapor included, then this becomes more complicated because we need to take it into the consideration. So after this, what I wanted to introduce is, now I want to simplify the evolution of each atmospheric variables. The first one is we come back to the temperature profile or the temperature evolution. Okay, so for temperature profile, we just keep it below 32 kilometers. Okay, just below that one, and then we come back to the evolution here. So below 32, so it has 3 parts, right? The first part is it decreases with the height increases. The second is it keeps constant. The third one is it increases with the increasing of the height. So 3 parts. The temperature profile can be expressed as, first one is the temperature at the sea level minus, right, a constant with respect to the times the height or the altitude, and then it is constant at 11. The third one is it evolves from 11 kilometers and increases according to this one. So this one is theta greater than 0, smaller than 11 kilometer. This is it as 11 kilometer, greater than 11 kilometer, smaller than 20 kilometer. This one is larger than 20 kilometers, smaller than 32 kilometers. So this is the temperature, and A is the same thing. A is the temperature lapse rate, right? So here is the temperature lapse rate is the correspond. So and this is for the condition here. So for standard atmosphere, A is equals 6.5 Kelvin per kilometers, and T11 is T node. It equals to 88.115 Kelvin. So it corresponds to 25 degrees centigrade, right? So in our theoretical calculations, if we do not have some specific requirements, we already set the temperature at sea level is around 25 degrees centigrade. So this is the calculations for the definitions for the temperature profile. Another parameter is density profile, the air density. Okay, and we name it as rho air to represent it with respect to theta. So it can be expressed as at sea level, it is around 1.225, right? At times, because it evolves exponentially also with respect to the height. So equals H1 here, name it. So H1 is around H1 is around 9.5 kilometers here, and it is named as the density scale height. So this is for the definition of it when the theta is smaller than 10 kilometers here. So how about if we wanted to increase it or extend it to be a much higher height? Then this equation have another expression, a little bit more complicated, 1.225 e minus theta over h2 times 1 plus 0.3 sin 0.3 sin theta over h2, like this one. And h2 is also called the density scale height, and it's 0.7.3 kilometers. Okay, and for this condition, it works when theta is smaller than 30 kilometers. More general expression for it now. So this is the density profile, and the last one is the pressure profile. So for the pressure profile, the first thing that so for the thermodynamics, there is relationship that it keeps always for the air when its temperature and its volume times its volume equals the temperature, the pressure times volume equals the temperature times is the Moore number and the times the constant R here. So the R is called the universal gas constant. Okay, and we want to we can do as we push the V moves to the right side, and it's gonna become the perform as P equals rho air times R times T divided by mass. Okay, this is mass of the atmosphere, the molecule, and rho air is the density, and R is the gas constant, the universal gas constant, and T is the temperature here. And Ra is really for the standard atmosphere. It is around 2.87. It is constant. So the pressure can be expressed as 2.87 rho air times temperature multiplied by m here, and it can be further evolved and get rid of h. So, for example, we can represent it to be, oh sorry, this is not here. This is this is r. So r over m is ra times layer times t. This one. So this is a general expression, and as we mentioned previously, it evolves. Or it decreases exponentially with respect to the height. With respect to the height, right? So this one is the left, which also the pressure scale parameter here. Again, also or the pressure scale height. So this is the expressions for the pressure here, and after that, we're going to see how the gas going to absorb the electromagnetic waves, because it is due to the internal electronic absorption or the vibrational or the rotational between the atoms or the molecules inside of the atmosphere. So we're going to introduce this after a short break. Okay. let's continue this part. So, the absorption and emission by gases. We know that the gas is going to absorb the electromagnetic waves, all right, and exert attenuation, the power loss on the channels, the radio channels or the communication channels. How is the emission? So for the emission, it's related to the black body radiation. So for any objects, when its temperature is above the absolute zero, for example 0 Kelvin, it's gonna radiate electromagnetic waves, right? So it can be detected by the radiometers. Okay, for the energy, so first thing is we just consider an individual molecule. Okay, for an individual molecule, for example, for the water or water vapor, it has hydrogen atom and 2 oxygen atoms, right? It's like this one. And so these are the bonds, right? So and when we take the equivalent center of both oxygen atoms, its center is here, right? At this point. So these molecule is kind of pole molecules, right? So it can be regarded as a dipole, right? So because this one is more almost, it has as charges corresponds to positive and its charges corresponds to negative. So it can work as dipole. So this is not what we want to use here. That's a short review. So for the internal energy of a molecule is internal. Energy. We use the epsilon to represent that, and it can be expressed epsilon E plus epsilon V plus epsilon R. Okay. The first one is called electronic energy. So for the electronic energy, it refers to the energy associated with the electrons in an atom or molecule. This energy is quantized and comes from arrangement of electrons in different energy levels. So for an image, so put an image in your mind, we can show it like this one here. So according to the atomic physics or the quantum mechanics, maybe some of you guys familiar with this. For an atom, it has the positive charge, right? And the electrons rotate around the positive charge, and it has different kinds of levels, right? So according to the quantum mechanics, in the first layer it has only 2 electrons, right? 2, 1, okay. And the second is 2, 2, that's 4, and all right, and then it decreases, all right, exponentially. For the electrons, it has different levels. It's going to have different energies, right? So, for example, it rotates around the positive charge. It's like this: the Earth rotates with respect to the Sun, right? So it can be expressed as it has its own energy, and when it moves, for example, this one, it moves in the n equals 1, this layer, the first layer, it won't move to the second layer. So the second layer has its own energy level also. It's going to absorb the electromagnetic waves. For example, this mechanism is first proposed by Einstein, all right? So it is called the electromagnetic, the optoelectronic mechanisms or the effect. And Einstein observed this mechanism, and he got the Nobel Prize, right? His Nobel Prize is not based on the relative theory, but it's based on the optoelectronic theory, effect. And he just observed that and take a relative simple theoretical analysis on it. However, there is another guy who proposed that. His name is called Bohr, all right? So Bohr. He is the founder of the electromechanics, and the most favorite thing is for his Bohr's formula. And it can be expressed as the when h for an electron it moves from epsilon 1 to epsilon m, a different energy level, it needs to absorb the energy. For example, it accepts the radiation by electromagnetic wave with the frequency of F node. There's another thing as H, alright? H is Planck constant, which is proposed by Planck, alright? So the Planck constant, that means it is the minimal element for our space. For example, for quantum mechanics, it tries to separate our physical world to be. It assumes that our physical world cannot to be separated to be infinitesimal elements, right? Because the most smallest, for example, the smallest components as the elements as Planck constant. So it is constant here. And for the proposal of this parameter, the Planck got the Nobel Prize, of course. So this is for the electronic energy, and here is for the vibrational energy. So, for an atom, when it moves from one layer to another layer, it corresponds to the variation of the electronic energy, and also it corresponds, there are several vibrational energy and the rotational energy corresponds. So, for the vibrational energy is because the rotation of the atoms, or the electrons, it rotates and not rotates, it vibrates. So it is associated with the vibrational motion of the atoms within a molecule. So molecules are not static, right? For each thing, even for a solid object, the molecules are not static. It vibrates and rotates. So for the vibrates, the atoms, they oscillate around their equilibrium positions, and these vibrational modes correspond to specific frequencies and like the electronic energy. So the vibrational energy, each are more quantized, and when a molecule absorbs the energy that lies between the infrared region, the spectrum, and it can undergo the transition between vibrational energy levels. Alright, according to the quantum mechanics, there are also vibrational energy levels and the rotational energy levels. For the vibrational energy levels, it corresponds to, if it moves from one energy level to another, it corresponds to the energy level inside our infrared region. And also for the rotational energy, is due to the rotation of molecule around its central mass. the molecules can rotate in different axes, and the energy associated with this rotation is quantized as well also. So the rotational energy levels, it depends on the moment of the interior of the molecule and are relevant in microwave spectrums. So these are three energy levels, and this energy level is much more simpler as it lies in the microwave regions. Here, it's a microwave region. Okay, so now if we can say that the electronic energy level is larger. It's larger than the rotational energy level, and the rotational energy level is larger than the vibrational energy level, and the vibrational energy level is larger than the rotational energy level. So when we come back to this term, it's like this one. So here is the electronic and the vibrational and the rotational here. So for each electronic energy levels between these two, we can separate it into several different kinds of vibrational energy levels, and for each two vibrational energy levels, they can be separated to the rotational energy levels, and this corresponds the number of each one. It depends on the atom numbers in each of their atoms, the electron numbers, sorry, and it depends, and it's related to the atomic physics. So I will not introduce the details of this one. So now we see that this one is much larger than this one, this one is much larger than this one here. So how large it can be? So for this one, the energy level between the energy difference between two levels, it lies in the range of 2 to 10 electron volt. Okay, and so electron volt means it corresponds to the electric charge times the 1 voltage, right? So it's also a unit for energy, all right? So it equals 1.6 times 10 to the power minus 19 joule. So this is for the difference for this part, and the difference for the vibrational energies for two neighboring energy levels is around 0.1 to 2 electron volt. And for the rotational energy levels, it's much smaller. It's 10 to the power minus 4 to 5 times 10 to the power minus 2 electron volt. So that means here, when the atoms or the electrons are going to transit from one energy level to another energy level, it needs to absorb a radiation in this range, all right? And when it rotates between two transitions between two vibrational levels, it needs to rotate the energy in this condition. And for the rotational energy levels, it's also something like this one. However, if we have an energy level, for example, the H mu, the radiation by electromagnetic wave is around maybe 3.05 electron volt, then it can be separated into the electron voltage around, for example, maybe 2, and for the vibrational as 1, and for the rotational as 0.05. So it corresponds to if the electronic transitions occurs. It corresponds to the traditional vibrational transitions and the rotational transitions. So basically we are together with each other. If there is only vibrational transitions, then it follows also the rotation position, but without this part. Okay. So now I wanted to propose how the energy levels absorbed. So for an example, we have the absorption port. As we mentioned previously, for the water vapor, it has two absorption lines. The first one is at 22. The second one is 183 gigahertz, right? So for the water vapor, as an example, so this is frequency in gigahertz, and this one is absorption. This is 22 gigahertz, right? This is 183 gigahertz. So according to our previous demonstrations, it should be a sharp lines. Should be sharp lines like this one. But however, when we come back to this plot, we can see for the water vapor absorptions, it has a broadened line, all right? And a broadened line. It's not a sharp line like this one. It's a broadened line. So it looks like this one. It's a broadened line like this one, right? So what's wrong with this one? Why it becomes broadened? A line broadening occurs. Why there is a line broadening? There are several reasons. Because as we mentioned previously, the molecules, they are not static. They move due to movements and rotations, vibrations, and colliding, right? For the molecules in air, they are also colliding, and this leads to some kinds that absorption lines at here, at here, at here, at here. There are many broken lines, even though a slime strength becomes smaller, but it moves around the designed frequency, and the oscillation moves like that one, and then the absorption lines is broadened. So this is for the absorption. And how we use a theoretical model to represent that? So we need a theoretical model to represent it. We need to come back, take a short review. So for example, as we all know that when we want to define the propagation of electromagnetic waves, all right? right? We get the solutions of the electric field, right? Which corresponds to the propagation of the electromagnetic waves, and the K represents the propagation of the electromagnetic waves, right? The K is the wave number, and when this is corresponds to lossless medium, all right? So there's no attenuation inside of the medium, so there's no absorption. However, when we transfer it to a lossy medium, we use another parameter to represent it, right? We use gamma square to represent K square minus, and that equation becomes minus gamma square times E equals 0, alright? So we get the expression, the solutions of it is E equals, for example, beta E minus gamma beta, like this one, alright? So gamma is called the propagation constant, and it can be expressed as J omega square root mu epsilon, alright? So for our conditions, we simplify it as because this medium is not a ferromagnetic medium, so the permeability equals that of the vacuum, alright? And we use our, because the dielectric constant becomes a complex value, so we use it as epsilon naught in vacuum, and this one is the relative permittivity, alright, or the relative dielectric constant. So this term is related to the speed of a light in vacuum, alright, so it can be expressed as J omega or C times square root epsilon. As we all know, the square root of dielectric constant is named as the refractive index, alright, that corresponds to the refractivity of the electromagnetic waves, and because it is a lossy medium, so the refractive index is a complex value, so it has a real part and an imaginary part here. So because the real part for the air at sea level, n prime equals 1.0003. It's a little bit higher than 1, alright? So we wanted to express it as 1 plus constant values we name it as n prime times 10 to the power minus 6, and n prime is called refractivity. Okay, and also this term is the same thing. This term is the imaginary part, so it only has the imaginary part here, like this one. Okay, so now we have the expressions for our refractive index, and the total complex part is called 1 plus 10 minus 6n, and n equals n prime minus j n double prime, double prime. So this is for the expressions of this one, even though you think, oh, why it is so complicated because it can help us for the calculations later. After that, our propagation constant gamma can be expressed as a value as j times 2 pi f. Alright, it's 2 pi f equals omega times c times n times equals j 2 pi f. 3 times 10 to the power 8 n prime minus j n double prime. Alright, and so the propagation constant also related to alpha plus j times beta, right? Could you remember this? Could you remember how alpha represents and how beta represents? Alpha represents to be the absorption by the medium, so it is called absorption constant, right? And the beta relates to the refraction, so it is called a phase constant. So that means that propagation constant is related to the absorption and the phase, or the refraction. So now alpha and beta can be represented by this part is omega c. Okay, alright, omega c times n double prime. Alright, and this beta equals omega c times n prime is the refraction, the real part, and this is related to the imaginary part. So now we know that if we get the refractive index of a medium for electromagnetic waves, its real part is related to the absorption, and the imaginary part is related to the absorption, and its real part is related to the phase propagation, the phase constant, or the refraction. And this can be further expressed as 10 to the power minus 6 omega over c n double prime. This can be expressed as 10 to the power minus 6 omega over c times 1 plus 10 to the power minus 6 n prime, like this one. So this is the expressions for the absorption and for the phase constant. This is related to the electric field. Alright, so for the electromagnetic waves propagation, we will more concentrated on the energy or the power. So we have the expressions for the power density. The power density is related to for the Poynting vector. Here we just concentrated on as the scalar part. It's related to the maximum times it evolves with respect to the propagation distance, right? And here as the absorption constant. Okay, and because alpha is just for the electric field, so for the power we have the electric field as square. All right, so we need a 2 here. So that means when I give you the refractive index of a material, I wanted you to calculate the power loss when the electromagnetic wave is propagates inside. You need to calculate that based on this equation here, and you need to use the refractive index, the imaginary part of it, to calculate alpha, and based on alpha to calculate this term. So this equation is very important, and this is only valid when the medium is uniform. For example, the atmosphere, right? It is uniform. So we would want to define another parameter as kappa A to represent that it equals 2 times alpha. And as unit is usually in Newton per meter, okay, as standard unit here. However, if I want to calculate that to be expressed to be in dB per meter, so how to get it from Newton per meter to dB per meter? We need to times 4.34 times 10 to the power 3 times this one equals dB per meter like this one. So we really wanted to transfer it. So then you calculate the absorption coefficient. This is absorption coefficient. So I express it into the dB per meter. So we use times 4.34 times 10 to the power 3 to calculate that. Okay, now we get the general expressions for the absorption by the water vapor and oxygen. So 8 of them. So how the gas, the total power loss, Ka, we transfer it to the Kg. Okay, the total power loss by the atmosphere. It is most related due to the H2O, water vapor plus oxygen. Okay, this is the expressions for this one. So we need to calculate the terms alpha H2O and alpha oxygen, right? And these two terms are related to the refractive index divided by oxy H2O and divided by oxygen. Right, then we can calculate the attenuation by that one. Actually, we have another form based on the measurements. So, as we mentioned previously, that for the water vapor, it has 2 absorption peaks. For the oxygen, it has 2 absorption peaks also. And we can see the width becomes broadened, right? The line is broadened here, the broadened here, broadened here. It's not even very much and broadened here. So the broadening means there are several other absorption lines beside the designed absorption line, all right? There are several other lines, so that means the same thing for here. For the water vapor, there are 34 absorption lines. And for the oxygen, there are 44 absorption lines. So that means for the oxygen, it can be represented by frequency J equals 1 over 44 times SI times FI. SI is the line strength. We add them together. The line strength, and Fi is the shape function. Add them together. We add these 44 absorption lines together. We can get the absorption spectrum by the oxygen. And the same thing for the water vapor. It can be expressed as 0.182 F times sigma j corresponds to 34 observation lines as I times fi. The same thing, but it has another thing is critical point above that frequency range, or it is outside of the frequency range for what we call in a very high region. So this is the difference is this term, or what we call here. So how to say the evolution of this point? This is for the oxygen. Okay, so when we come back to say it, zoom in for oxygen from this point, we just take this point. Okay, we zoom it in. We zoom in this point, and we can see there are many absorption lines. Okay, many absorption lines. So all these absorption lines contributes to the total absorption by the oxygen, and also the same thing for the water vapor. Another thing that I wanted to show you guys is that we can see there is a difference between these two curves, alright? Here we can see even the data from 20 to 30 kilometers, and here is from 0 to 32 kilometers. So that means here it offers a much larger height range, right? 0 to 32. This is just a smaller height range, is 20 to 32. But if we want to mirror the absorption lines and separate them, we would want to use this condition, right, instead of this condition. Why? That's because under the ground, not under the ground, closing to the ground, under the 20 kilometers height, there are many disturbing components. This gonna makes the observation of the absorption lines to be not so obvious. So that's why we wanted to take measurements on the oxygen and water in the atmosphere at high altitudes, such as in the North Pole or the South Pole, or in Tibet, right, at very high mountains, right, on the top of the high mountains, because we wanted to get rid of the disturbing from from the ground to 20 kilometers. Okay, and so there is another parameter that we wanted to introduce. It is called, so if we wanted to see how this part is going to block or going to affect the transparency of the electromagnetic waves, we call it to be, we call it to be the opacity. Of the clear atmosphere. So opacity, that is opposite to the transparency, all right? Opacity, that means the blockade corresponds to. The transparency means the transmission through, all right? So for opacity of atmosphere layer, for example, from the height, from the height of theta 1 to theta 2, we name the optical thickness is theta node, theta 1, theta 2, like this one, these two sides, okay? However, mostly our observation or our radiometer, the channel, is not perpendicular to the atmospheric layers, right? It has a slant path like this one, right? With the zenith angle as around theta, for example, and we call it oblique opacity, optical thickness, or opacity. We call it, okay, this is not theta, this is tau. Oh, so this is tau, theta 1, theta 2 times equals tau node, okay? Node. Theta 1, theta 2 divided by cosine theta. And it equals tau node, theta 1, theta 2, set theta. Alright? So this is the optical thickness related to the opacity. So how to, now we know the theta and we can calculate the oblique optical thickness with respect to any kind of the zenith angle. How to obtain this term? There is a calculation as the zenith optical thickness. It can be expressed as based on the absorption coefficient from theta 1 to theta 2. Take integration of each and calculate the optical thickness of it. So how, if we wanted to get the transmittivity, for the transmittivity corresponding to this term, the transmittivity, we use this term to represent that. It can be expressed as e to the power minus tau theta 1, theta 2, from theta 1 to theta 2. It can be expressed by this equation like e minus tau theta, theta 1, theta 2, set theta to represent the transmittivity here. So now, based on the refractive index, all right, we can calculate the absorption constant and the phase constant. And for the absorption constant, we can get the absorption coefficient kappa A. And from the absorption constant kappa A, we can calculate the optical thickness and also the oblique optical thickness. And based on oblique optical thickness, we can calculate the transmittivity based on this question. All right. So now for this lecture, we try to introduce the just a basic parameter for the mediums for the atmosphere, which is regarded as medium. All right, because the atmosphere is a gas. It can be regarded as a uniform medium, and its refractive index is the distribution of uniform. The distribution of its refractive index or the dielectric constant is uniform, and we can calculate the absorption constant and the phase constant and all the refractive index or the refraction performance of it, and we can calculate the transmittivity or the opacity of the clear atmospheres on the electromagnetic waves. So why we wanted to calculate this? Because we wanted to calculate how much the signal is backscattered by the atmosphere and how much the power is absorbed by the atmosphere when it propagates through the atmospheres. So this is very important for our future calculations for the channel modeling. And I think I would want to introduce how the gases absorbs the electromagnetic waves after this lecture and after next lecture, okay? And for next lecture, we're going to introduce the other atmospheric constituents, such like the weather constituents, such like the rain, snow, and the air bubbles. So I think that's all for this lecture, and I'm going to see you guys next week.